Usually, when we think about just taking a step, there's this incredibly ingrained expectation of top-down command.
Right, like a corporate hierarchy or something.
Exactly. It feels like the CEO, your brain, makes a conscious decision, sends an email down the neural pathways, and the workers at the bottom just execute the task.
Yeah, it feels entirely conscious. I mean, you look across the street, see a coffee shop, and decide you want an espresso.
And you just assume your brain is explicitly orchestrating every single microcontraction of your quads and calves to get you to that door.
It's an illusion of pure will. Because when you actually step into the landscape of motor circuits, specifically the neural mechanisms of locomotion, that corporate hierarchy model just shatters.
It really does. The physiological reality is so much more decentralized than we feel it is.
Oh, entirely. The spinal cord isn't just some bundle of passive wires taking orders. It has this intrinsic autonomous intelligence.
Which is exactly the core revelation we are dissecting today. Welcome back to our ongoing deep dive series, everyone.
Yes, continuing our journey through the fundamental principles of neuroscience.
Right, and specifically, we are still living in part 5 of Candle's textbook. The overarching theme for these sessions is movement.
And part 5 is massive, right? It's divided into chapters 30 through 39. So this is just one piece of a much larger ongoing series of deep dives on movement.
Exactly. Today is chapter 33, which is totally dedicated to how the nervous system coordinates the act of walking, swimming, and running.
And since this deep dive is tailored for fellow neuroscience learners and professionals, I want to establish our pacing right up front.
Yeah, this is a rule for us today. The pace will be deliberate. It will be unhurried.
Right. There is no rush. We're dealing with heavy, highly technical material, and we need a fluid, slower rhythm so you can really grasp the molecular and cellular realities.
We want you to fully comprehend this. So to set a framework for everything we're about to unpack, if walking is a car journey, your brain is not the engine.
No, not at all. The spinal cord is the engine.
Right. The brain is just the driver. It decides the destination, maybe taps the gas pedal, steers around a pothole.
But the raw, rhythmic, mechanical generation of power, that churning of the pistons, that lives entirely within the spinal cord.
It's just wild to think about, but to appreciate how autonomous that spinal engine is, we really have to look backward first.
Yeah, we have to look at the evolutionary foundations across species. I mean, locomotion is arguably one of the most fundamental, highly conserved behaviors on Earth.
Right. From invertebrates all the way to humans, that underlying alternating rhythm is remarkably similar.
But obviously, to study that, you can't just put a human in an fMRI scanner and say, hey, go for a jog.
No, the spatial and temporal resolution of an fMRI is way too slow for that. You can't capture the millisecond by millisecond firing of a single motor neuron.
Let alone the physical constraints of trying to run inside a giant magnet.
Exactly. So the field has developed a very specific experimental toolkit. There are really 4 primary preparations used to decode this.
Yeah, let's lay those out because the methodology literally defines the discoveries.
The first one is straightforward. It's the intact preparation.
Right, the baseline. You study normal, unimpaired behavior, usually by implanting EMG electrodes directly into the animal's muscles.
And you pair that with high-speed kinematic video. It gives you the map of exactly when the flexors and extensors fire during a healthy stride.
But observation only gets you so far,
Right.
To understand the mechanism, you have to start isolating variables.
Which brings us to the decerebrate preparation. This one is intense.
It is. You surgically transect the brainstem, usually right at the midbrain. You physically disconnect the cerebral cortex and basal ganglia from the spinal cord.
And the historical shock of this cannot be overstated. Because with no cerebral cortex, no conscious thought whatsoever, what happens?
Well, if you place that decerebrate animal on a treadmill and stimulate the remaining brainstem, it walks.
It just walks. A perfectly coordinated gait without a brain to plan it.
Exactly. It definitively proves the motor cortex is not required for the basic rhythm of stepping.
Okay, so if the brainstem can drive the cord, the next logical step is to remove the brainstem entirely, right?
Right. That's the third method, the spinal preparation. You sever the spinal cord completely, usually at the lower thoracic level.
So the hind limbs are completely cut off from any descending brain signals at all.
Yep. And yet, with the right pharmacological stimulation, or even just sensory feedback from the treadmill belt, those isolated hind limbs will still produce a rhythmic stepping pattern.
It is the ultimate proof of the engine analogy. The engine runs even when the driver is totally missing.
And if you want to look at the literal nuts and bolts of that engine, you go to the fourth method.
The in vitro preparations.
Right. You extract the isolated spinal cord of a neonatal rat, or a tadpole, or a lamprey, and keep it alive in artificial cerebrospinal fluid.
You essentially just watch the spinal cord walk in a petri dish.
Yeah, and the lamprey model has been particularly revolutionary. It's a jawless eel-like fish.
Which swims with this undulating wave of muscle contractions. And its spinal cord is anatomically much simpler than a mammal's.
Plus, it's highly resilient to hypoxia, so it's super stable for long-term study in a fluid bath.
Okay, I have to push back here for a second, just from a clinical perspective.
That's right.
If the ultimate goal of reading Candle is to understand human locomotion like a bipedal ape balancing against gravity, aren't we losing too much complexity by studying a fish in a dish?
It's a totally fair critique. Early researchers debated that constantly, but the defense rests entirely on evolutionary continuity.
Meaning nature doesn't like to reinvent the wheel.
Exactly. The nervous system rarely invents totally new architectures. It just adds layers of modulation onto a really successful core.
So you're saying human walking is fundamentally just heavily modulated fish swimming?
At the level of the rhythm generator, yes, absolutely. By looking at the lamprey, you strip away gravity and complex limbs with knees and ankles.
Leaving just the pure rhythm, the need to alternate left, right, and front, back.
Right. Once we decode that pure core in vitro, then we can figure out how the mammalian cortex adds its complexity on top.
That makes a lot of sense. You have to isolate the fundamental oscillation. So let's look at the physical output of that oscillation.
The step cycle itself, it's mathematically beautiful.
At a macro level, it's just two phases, right? The swing phase, where the foot is in the air, and the stance phase, where the foot is on the ground.
Yes, providing the propulsive force. But as neuroscientists, we have to look closer. We have to divide that step into 4 highly distinct subphases based on joint angles.
Okay, let's map it. It starts with flexion, or F.
Right. The swing phase begins with F. The flexors of your hip, knee, and ankle all contract together to lift the foot and accelerate it forward.
But the swing phase doesn't actually end with flexion, does it?
No, and this is crucial. While the foot is still traveling through the air, you enter the first extension phase, E1.
This detail totally reframes how I think about movement. Wait, the extensor muscles are aggressively firing before the heel even strikes the ground.
Exactly. The nervous system isn't waiting to hit the ground to react. It's actively predicting the ground.
That's incredible. The spinal cord is initiating an anticipatory brace.
It has to. Because the millisecond your foot actually makes contact, the physics of the system radically change, and we enter the E2 phase.
A yielding phase.
Yes. As your body weight violently transfers onto that leading leg, the knee and ankle actually flex slightly, even though the extensors are still firing intensely.
So the extensor muscle is generating massive force, but the sheer weight of the body forces the muscle fibers to physically lengthen.
Right, it's an eccentric contraction. And it serves as a biological shock absorber.
Because if the legs stayed perfectly rigid, the kinetic impact would just send a devastating shock wave right up your spine.
Exactly, you'd shatter your joints. So the E2 yielding absorbs that energy. And only then do we transition to E3.
Where the hip, knee, and ankle all forcefully extend together to actually push the body forward.
Right, so that 4-part sequence, F, E1, E2, E3, that describes intralimb coordination, just the timing within one single leg.
But obviously we have more than one leg. We have to coordinate the left with the right, interlimb coordination.
And neurophysiologists quantify this using phase differences. If a full step cycle is a value of 1.0, a phase difference of 0.5 means the limbs are exactly out of phase.
Like alternating. When the left leg is halfway through, the right leg is just starting.
Exactly. That's the standard human walk or a cat trotting. But a phase difference of 0 means perfect synchronization.
Like a rabbit hopping or a horse galloping.
And the remarkable thing is, the isolated spinal cord can shift between that 0.5 alternating phase and a 0 synchronous phase purely based on the intensity of the drive it receives.
Without the brain needing to recalculate anything.
No brain required.
Which brings us to the central mystery of this chapter. If the muscles anticipate the ground, and the phase differences happen automatically, where is the timing coming from?
Yeah, what is the physical nature of the spinal engine? It all comes down to the central pattern generator, or the CPG.
A massive paradigm shift in motor physiology.
Huge. Because you have to remember the old paradigm, driven by people like Charles Sherrington. They thought locomotion was just a complex chain of reflexes.
A purely reactive theory. You step, the stretch triggers a sensory reflex, which lifts the leg, which triggers another reflex.
Right. Sensory feedback was thought to be the generator. But in 1911, Thomas Graham Brown completely destroyed that theory.
Let's talk about that experiment. He transected a spinal cord to remove brain input, and then he did a deferentation.
He surgically cut all the dorsal roots of the spinal cord, the exclusively sensory pathways.
So zero sensory information from the limbs could reach the cord. No muscle stretch, no skin pressure, totally deaf and blind.
Under the old reflex theory, that spinal cord should have been dead silent. No sensory triggers means no movement.
But it wasn't silent.
No. He observed that the completely isolated, sensory-deprived spinal cord still generated a robust, alternating rhythm of flexor and extensor firing.
Unbelievable proof of intrinsic neural intelligence. It's an innate property of the circuitry.
So to explain this, Graham Brown proposed the half-center model. He hypothesized that spinal interneurons were split into two functional halves.
One half center exclusively for flexors, one for extensors. And it relies on mutual inhibition, right?
Yes. When the flexor half center is active, it doesn't just stimulate flexors. It sends powerful inhibitory signals across to completely suppress the extensor half.
But neurons fatigue. They can't fire at max capacity forever.
Exactly. The flexor half slows down, its inhibitory grip weakens, and the resting extensor half escapes the suppression.
It springs into action, fires the extensors, and inhibits the flexors. It's a biological seesaw.
An endless alternating rhythm.
Dar.
Now, it was an elegant model, but as computational neuroscience evolved, we realized it was a bit too simplistic.
It mashed the creation of the timing and the distribution of the signal into the same group of cells.
Right, which led to the updated framework,
Yeah.
the Ryback two-layer model.
It separates the CPG into a rhythm generator layer on top and a pattern formation layer below it.
I love the symphony orchestra analogy for this.
Oh yeah, it's perfect. The rhythm generator is the conductor at the podium. They don't play an instrument, they just set the tempo. Tick-tock.
They determine the overarching duration of the swing and stance phases.
And the pattern formation layer represents the sheet music and the musicians. It takes that general beat and distributes it to specific motor neuron pools in a very specific sequence.
It tells the ankle extensor to fire exactly 12 milliseconds after the knee extensor, for instance.
And this two-layer model perfectly explains how certain sensory inputs can alter muscle force without changing the overall walking tempo.
Exactly. Because the pattern layer is tweaked while the rhythm layer is unaffected.
Okay, so these models are great in theory. But how did we prove this physiological reality?
That takes us to the 1960s. Anders Lundberg's group in Sweden took spinalized cats and injected them intravenously with L-dopamine.
Right, L-dopamine is a precursor to dopamine and norepinephrine.
And in a healthy animal, descending brainstem pathways release those exact neuromodulators to turn on the CPG.
So by injecting L-dopamine systemically, they artificially mimicked the brainstem.
And the result was fictive locomotion. The completely severed spinal cord just woke up and started firing a perfect walking rhythm down the motor nerves.
The clinical implications of that are staggering if you think about spinal cord injury and paralysis.
The neural blueprint for walking still exists below the injury.
Right. Curing paralysis isn't necessarily about teaching the brain to walk again or regenerating millions of cortical axons perfectly.
The engine is fine. It just lacks the ignition key. We just need to find the right surrogate to replace that lost on switch.
But to build that surrogate, we need to know exactly what the engine is made of at a microscopic level.
And this is where modern developmental neurogenetics comes in. We can now track specific transcription factors during embryo development.
We aren't just probing random pools of interneurons anymore. We can genetically classify them into families.
Yes. The primary families in the ventral spinal cord are V0, V1, V2A, V2B, and V3 interneurons, and each has a very specific job.
Let's break them down, starting with interlimb coordination. Obviously, your left leg needs to know what your right leg is doing.
Right, and that requires axons to cross the physical midline of the spinal cord. Commissural interneurons.
And those are the V0 interneurons.
Specifically V0D and V0V. They cross the midline to make sure the left and right sides maintain that alternating 0.5 phase difference.
And the genetic knockout studies for this are wild. If you engineer a mouse without V0 interneurons, what happens?
The basic rhythm still works. It moves its limbs, but it completely loses the ability to alternate.
It just hops like a rabbit at every speed.
At every speed.
Yeah.
Synchronous hop. Without the V0 neurons shouting across the midline to wait, both sides just default to firing simultaneously.
Incredible. Okay, so V0 is left to right. What handles flexor to extensor coordination within one leg?
That's the V1 and V2B interneurons. These are ipsilateral, meaning they stay on the same side of the cord.
And they are mostly inhibitory. They are the physical embodiment of Graham-Brown's mutual inhibition.
Exactly. When flexors fire, they violently suppress the extensors. If you ablate both V1 and V2B, reciprocal inhibition vanishes.
Flexors and extensors fire at the same time, locking the limb into a rigid spastic extension.
So we have the left-right wiring and the flexor-extensor wiring, but who is the conductor? Who drives the rhythm?
The core rhythm generator candidates are subsets of glutamatergic interneurons, defined by SHOX2 and HB9 transcription factors.
And these specific neurons have intrinsic pacemaker properties.
Okay, I really want to dig into the biophysics here. What does a pacemaker property actually look like in a cell membrane? How does it autonomously turn itself on and off?
We have to look at the ion channels. Let's start with a resting SHOX2 neuron. It gets a generalized excitatory signal glutamate binding to NMDA receptors.
And NMDA receptors are fascinating. They are both chemically gated by the glutamate and voltage gated.
Right. At rest, the pore is literally plugged by a magnesium ion.
But the ambient glutamate causes a slight positive depolarization, which literally kicks that magnesium plug out.
And once it's unplugged, a massive influx of positively charged calcium rushes into the cell.
Driving the membrane voltage way up, triggering a plateau potential, the neuron bursts rapidly. It's on.
But it can't stay on forever or the muscle cramps. It has to turn off and pass the baton.
So how does it force itself off?
The elegance here is that the calcium that turned it on is also the trigger to turn it off. As calcium accumulates inside, it binds to calcium-activated potassium channels.
And potassium is highly concentrated inside the cell, right?
Yes, and it's positively charged. So when these channels open, positively charged potassium rushes out of the cell.
So if positive ions are leaving en masse, the inside becomes rapidly negative again. It hyperpolarizes.
The plateau potential crashes. The cell turns off. It essentially chokes on its own metabolic exhaust.
That is beautifully poetic. And when it turns off, the reciprocal inhibition on the other half center is lifted,
allowing the other side to begin its own calcium-driven burst. But we have one final mechanical problem.
Right. Our first neuron is sitting in a deep, negative, hyperpolarized trough. How does it recover to fire again?
HCN channels. These are super unusual because they open in response to hyperpolarization, not depolarization.
So when the cell gets really negative, HCN channels spring open,
allowing a slow, steady inward leak of sodium and potassium. It creates a rebound excitation,
slowly creeping the voltage back up until, bam, the magnesium plug gets kicked out again.
And the cycle restarts. When you synthesize all of this, the macroscopic elegance of a horse galloping across a field
is ultimately governed by microscopic calcium and potassium ions flowing across lipid bilayers in the spinal cord. It's breathtaking causality.
It really is. But as perfect as this isolated clock is, we have to bring the real world back into the picture.
Right. A perfect clock is great on a perfectly flat treadmill, but the real world is muddy, uneven, filled with rocks.
Exactly. An autonomous clock that ignores the environment will just make you trip on your first step outside.
So how does the spinal cord adjust to reality? Sensory feedback.
The CPG generates the expectation, but the peripheral nervous system provides the hard reality.
The most critical sensory stream here is proprioception, the body's internal map of joint tension and muscle length.
The spinal cord relies on two very specific proprioceptive signals to safely transition from stance to swing.
Signal number 1. Hip extension. You have muscle spindles embedded deep in your hip flexors, innervated by E and C afferent fibers.
They are biological stretch sensors. As your body moves forward over a planted foot, the hip extends, stretching those front muscles.
And as the stretch hits a maximum threshold, those sensory fibers scream to the spinal cord, "The leg is trailing! It's time to swing!"
This directly excites the flexor half center. But hip extension alone isn't enough.
No, because imagine standing still with one leg stretched far behind you, holding all your weight. If it just flexed, you'd collapse.
Which introduces the second mandatory signal, limb loading.
Measured by the Golgi tendon organs, innervated by EVA afferents.
Right. While muscle spindles measure stretch, Golgi tendon organs measure physical force or load.
So as long as your foot is bearing weight, the extensor muscles are under tension, and those EVA afferents are firing continuously.
And they act as a massive physiological stop sign. They tell the CPG, do not lift this leg under any circumstances.
They excite the extensors and inhibit the flexors.
So to safely initiate a swing, the spinal cord requires a sensory consensus. The hip must be extended, and D, the physical load must be removed as weight shifts to the other leg.
Only when both conditions are met will the rhythm generator allow the transition. It's a fail-safe logic circuit.
But proprioception only tells you about your own body. What about external obstacles, like hitting a hidden rock mid-swing?
Cutaneous mechanoreceptors in the skin of the foot and ankle handle that. It triggers the stumbling corrective reaction.
And this highlights what I think is one of the most brilliant computational hacks in the nervous system: phase-dependent reflex reversal.
Oh, I'm obsessed with this concept. Let's really build the scenario. Picture a cat walking across a room.
During the swing phase, its paw is in the air. If you tap the top of the paw with a probe, simulating a branch,
The immediate hardwired reflex strongly activates the flexor muscles. The cat reflexively bends its elbow to step higher over it.
total evolutionary sense. But here is the magic. If you take that exact same probe and tap the exact same spot on the paw,
But during the stance phase, when the foot is planted and bearing weight,
the reflex is completely inverted.
the nervous system reverses the output. Instead of flexing, the sensory input excites the extensor muscles. The leg stiffens.
Because if it flexed while supporting the animal's weight, the cat would collapse.
The astonishing thing is the sensory input coming up the nerve is completely identical in both scenarios.
Yet, they produce diametrically opposed motor outputs, because the interpretation depends entirely on the oscillatory state of the CPG.
The CPG is like a railway switch. In swing phase, it routes the signal to the flexors. In stance phase, it flips the switch and routes it to the extensors.
It's a context-dependent neural gate.
It's exactly like a smart home thermostat. If it reads 70 degrees in winter, it turns on the furnace to heat up. But if it reads that exact same 70 degrees in summer, it turns on the AC to cool down. Same sensory input, totally opposite physiological response based on context.
That's a very accurate analogy. So sensory feedback keeps the spinal engine tethered to physical reality.
But our car, with the perfect engine and sensory suspension, is still just idling. It needs a driver to press the gas pedal.
We need to ascend the neuroaxis into supraspinal control. We are looking for the accelerator pedal in the brainstem.
The mesencephalic locomotor region, the MLR.
The discovery of the MLR in the 60s by Mark Schick was a watershed moment.
They took a decerebrate cat, put an electrode into the MLR, and low-level stimulation caused the cat to spontaneously walk on a treadmill.
And the fascinating part is the relationship between the stimulation intensity and the output. It isn't a linear volume knob.
No, as you turn up the electrical dial, the gait snaps into discrete quantum leaps.
At low microamps, it walks. Turn it up, and it suddenly snaps to a trot. Push it higher, and the phase relationship's totally reorganized into a full synchronous gallop.
The MLR isn't sending complex timing instructions. It just sends a raw, continuous go signal.
And the spinal cord autonomously interprets that intensity to decide which gear to shift into.
And anatomically, the MLR is actually two distinct subnuclei, the cuneiform nucleus, or CNF, and the pedunculopontine nucleus, or NPP.
Both are glutamatergic, but they serve different contexts. The CNF sits a bit higher in the midbrain, and it's basically the panic button.
Right, highly associated with escape. You stimulate the CNF, the animal launches into high-velocity bounding, fleeing a predator.
But the MPP sits slightly lower, and stimulation there triggers slower, exploratory pacing, sniffing the environment.
So the MLR generates the drive, but its axons don't reach the lumbar spinal cord directly. They need a relay.
They synapse onto the reticular formation in the pons and medulla, and from there, the reticulospinal tracts emerge.
These massive tracts travel all the way down, using glutamate and serotonin to activate the spinal networks.
But the lower brainstem also has to manage the physics of movement, because walking is really just a controlled fall forward.
To keep us from face planting, the reticulospinal tracts work with the vestibulospinal tracts.
The vestibular nuclei are constantly getting data from your inner ear about your head's position relative to gravity.
And as your center of mass shifts, they rapidly adjust your extensor muscle tone to maintain equilibrium.
If you look at this macro architecture, the MLR is an incredible anatomical funnel.
Right. You have the basal ganglia involved in motivation and the cerebral cortex handling conscious intent.
And both of these massive forebrain structures converge down onto the MLR.
It's the ultimate bottleneck. Every conscious thought, like, I need to run to catch that bus, has to pass through the MLR.
The cortex formulates the goal, the basal ganglia permits it, but the MLR translates that abstract desire into a physical glutamatergic signal,
All conscious desire must become a brainstem reality before it becomes a spinal reality.
which paves the way to talk about those forebrain structures, because we don't just walk on flat treadmills.
We hike over rocky trails, we step over branches. For precise, visually guided locomotion, the automated spinal cord is not enough.
We need the heavy computing power of the motor cortex, the posterior parietal cortex, and the cerebellum.
Starting with the motor cortex. A decerebrate cat walks fine on a flat belt, but ask it to walk across a horizontal ladder with irregular rungs?
It fails completely. Its paws slip through the gaps. The motor cortex is indispensable for visually guided precision.
When you see a complex obstacle, the motor cortex fires transient bursts down the corticospinal tract, bypassing the MLR entirely.
It micromanages the motor neurons. Mid-swing, it can command a flexor to contract a fraction longer to land perfectly on a narrow rung.
But the motor cortex is blind. It needs spatial coordinates to know where to put the foot.
And that 3D model is built by the posterior parietal cortex, the PPC. It marries visual input with proprioception.
And the most astonishing feat of the PPC is spatial working memory, the ghost obstacle experiment.
Oh, I love this experiment. Let's describe the setup carefully. A cat is walking on a motorized treadmill.
A small physical obstacle approaches. The cat sees it and successfully lifts its front legs over it.
But the moment the forelimbs clear it, the researchers instantly cut the power. The treadmill stops dead.
The cat is straddling the obstacle, front legs past it, hind legs behind it.
Then, researchers silently drop the obstacle through a trapdoor in the floor. It's completely gone.
The cat waits there for seconds, sometimes minutes. Then they turn the treadmill back on.
And the behavioral readout is stunning. As the hind legs approach the empty space, the cat executes a massive high-stepping flexion
It expends significant energy to step cleanly over a ghost.
because its posterior parietal cortex actively maintained a perfectly scaled geometric model of that obstacle in its working memory.
It held onto the coordinates while standing still, updated them as it moved again, and fed them to the motor cortex to ensure the hind legs cleared a hazard that hadn't visually existed for minutes.
It proves locomotion isn't just real-time reaction. It's a continuously updated predictive model.
But predictive models can have mechanical errors. Muscles fatigue, surfaces are slippery.
Which is why we rely on the ultimate quality control processor, the cerebellum. It meticulously regulates timing and intensity.
By comparing two streams of data. First, it gets an efference copy of the intended motor plan via the ventral spinocerebellar tract.
Here is the exact step we intend to execute.
Simultaneously, it gets real-time sensory feedback from the proprioceptors via the dorsal spinocerebellar tract.
Here's what physically just happened.
The cerebellum compares the intent to the reality. If you slipped on gravel, the reality doesn't match the intent.
So it computes the mathematical error and fires rapid corrective signals to adjust the very next step.
This is beautifully demonstrated by the split belt treadmill experiment. The left belt moves at 1 mile an hour, the right at 3 mile an hour.
At first, the person's gait is chaotic and completely uncoordinated.
But within dozens of steps, the cerebellum processes the massive discrepancy and forcibly adapts the descending motor output.
Shifting the CPG phase timing until the person settles into a smooth, bizarre, limping gait that keeps them upright.
And a patient with cerebellar ataxia simply cannot adapt to the split belts. They lack the hardware to compute the error.
The final forebrain structure to integrate is the basal ganglia. They are the supreme arbiters of action selection,
Initiating and terminating complex motor programs, and we see their importance most devastatingly in Parkinson's disease.
right, which is characterized by the death of dopaminergic neurons, starving the basal ganglia of dopamine.
Dopamine is like a permissive lubricant. Without it, the basal ganglia's inhibitory pathways become pathologically overactive,
They project unrelenting inhibition down to the MLR.
leading to the classic shuffling gait and the profound clinical phenomenon of freezing of gait.
The patient has the conscious desire to walk. The spinal CPGs are perfectly healthy.
But the dopamine-starved basal ganglia acts like a jammed emergency brake. The engine is primed, the gas pedal is pushed, but the brake won't release.
It highlights how many delicate pathways must align for a single thoughtless step.
Which brings us to our final synthesis. We've talked a lot about quadrupeds. Does all of this actually apply to humans balancing precariously on two legs?
The short answer is yes. The evolutionary blueprint was adapted, not rewritten. The human lumbar spinal cord contains those genetically defined CPGs.
And the most charming evidence for human CPGs is the infant stepping reflex.
Yes, you hold a newborn baby upright so their feet lightly touch a table, and they instinctively make coordinated walking movements.
Which is profound because a 3-day-old baby's descending corticospinal tracts are completely unmyelinated and immature.
They have zero voluntary cortical control over their legs. The pattern is driven entirely by the spinal CPGs waiting for sensory input.
But we have to acknowledge the clinical difference. A spinalized cat can be induced to walk easily, but an adult human with a complete spinal cord injury cannot. Why?
It comes down to the brutal physics of bipedalism. A cat has 4 legs and a stable base. A human is an inverted pendulum.
We are inherently unstable, so hominins evolved to heavily outsource our balance control to the forebrain.
As we learn to walk, the developing cortex heavily infiltrates the CPGs just to keep us from falling over.
But the beacon of hope in neurorehabilitation is that those CPGs are still down there. They are just dormant.
And this physiological realization drives treadmill training with partial body weight support for spinal cord injury patients.
It's the literal translation of this candle chapter. Therapists suspend a patient in a harness over a treadmill, unloading some of their weight.
And as the belt moves, therapists manually move the patient's legs through the mechanical phases of the step cycle.
They aren't just stretching muscles. They are deliberately speaking the native language of the spinal cord.
Right. Forcing the leg into hip extension maximizes the IN2 sensory afferents.
Allowing the foot to strike the belt modulates the iapafferent signals.
They are manually feeding the mathematically required sensory consensus to trick the latent CPG into firing.
They're forcing the Ryback pattern formation layer to initiate a swing. And by doing this thousands of times, they harness neuroplasticity.
It strengthens remaining connections and teaches the injured cord how to run its own engine again. The clinical outcomes can be staggering.
It's the ultimate vindication of basic science. Decades of studying jawless lampreys in petri dishes translating directly into restoring human mobility.
A perfect synthesis of the molecular and the macroscopic.
So let's summarize this immense physiological journey. We traced a step from its dopamine-dependent initiation in the basal ganglia,
Mapped spatially by the working memory of the posterior parietal cortex, and fine-tuned for precision by the motor cortex.
funneled down through the accelerator pedal of the MLR, translating conscious desire into an intense glutamatergic drive,
To finally awaken the genetically hardwired machinery of the spinal CPGs.
where the biophysics of calcium and potassium flowing through VO0 and V1 interneurons beat out an oscillating rhythm.
A rhythm constantly tweaked by the real-time proprioceptive reality of the limbs striking the earth, all supervised by the cerebellum.
It's a masterpiece of decentralized neural control. And as we wrap up, I want to leave you with a provocative thought.
Let's hear it.
The next time you take a walk, pay close attention to your state of mind. You might be daydreaming or lost in thought about a research problem.
Your conscious mind is entirely elsewhere.
Yet your body flawlessly navigates concrete curbs, steps over roots, and maintains a perfect, alternating pendulum swing of your limbs. We cling to the illusion that our conscious brain is in total control.
But maybe, for a vast majority of our physical existence moving through the world, the brain is just a passenger enjoying the view.
And the spinal cord is the one truly driving the machine.
A deeply humbling reality to end on.
Thank you so much for joining us for this incredibly detailed session. This concludes our deep dive into Chapter 33 of Kendall's Principles on Locomotion. We really appreciate you taking the time to slowly unpack these circuits with us. We look forward to having you back for our next deep dive in this movement series.